Well, first, let me thank the organizer of this conference for giving me an opportunity to talk here. It's a real honor to talk at Amplitudes. And today I'm going to talk about a recursive approach to Landau analysis. And this is based on a work together with Simon Caron and Miguel Correa. So let me first set up the stage by considering arbitrarily complicated Feynman diagrams and can have many massive loops, many external legs. It can be non-planar, planar, it doesn't matter. And suppose that you're strong enough to actually evaluate the integrals that are associated to this diagram. What you're going to find is a probably very complicated function defined in the kinematic space, which means that it's a function that depends on these Lorentz invariant dot products between the external momenta and the internal masses that runs into the loops. And the question in its most general form that we're interested to ask is what is the analytic structure of this function? And maybe a more refined question is where are its kinematic singularities? And just to be sure that we're all on the same page, let's look at a very simple example that we can all integrate ourselves. So the bubble in 3 dimensions is given by this expression, and by kinematic singularities, I mean basically wherever this expression diverges. So clearly there's something funny that happens at s equals 0, and also whenever the log diverges. And this is a question that is very well understood at one loop, but can be very, very hard to answer beyond. And we already seen a few times this week that this could be enormously useful. So it's enormously useful to have a control over this question, especially in the Feynman integral program where we need to often use differential equations or numerical methods to solve Feynman integrals. And it's also very useful, as Andrew pointed out, for simple calculus and the bootstrap of Feynman integrals. I wanted to highlight one talk, so the talk by Samuel, where he told us that knowing singularities beforehand has actually proven very central in state-of-the-art calculations. So these two-loop 5-point with 2 masses example, knowing the singularities helps a lot dealing with the bottleneck of IBPs. So in general, it's convenient to cast the singularities into a list LG of polynomial LGI equals 0 in these variable xg and in the internal masses. And the product over I of these polynomial has a name. It's known as the Landau discriminant, and its job is to know about all the singularities of a graph G. And the goal of today basically is to learn how to compute these polynomials recursively, so how to compute these polynomials recursively in terms of those of the subgraph. And by subgraph, I mean simpler graph embedded into the original graph. So said differently, our goal is to find the prescription that basically allows us to glue the singularity of this graph and this graph together to get the singularity of the old graph. Yeah, that's the goal. So this is my outline. In the first section, I want to make this a bit more precise by introducing this recursion via unitarity kernels. Then I want to illustrate this using explicit examples. And I would like to conclude by enumerating some checks and some new analytic predictions that we were able to make using this recursive method. Yeah. So again, to put everyone on the same footing, I would first like to review the link between unitarity and thresholds, which should be somehow central to the argument. So unitarity of the S matrix tells us that S as dagger is equal to unity. And in practice, it's useful to separate S in terms of its free, so 1, and interacting part T. And when you plug this equation here, that's basically what you get. And for convenience, to streamline the discussion, I'm going to call the left-hand side of the unitarity equation the imaginary part of T, although there's some assumption that goes under the rug here. But the point is that at the end, these assumptions won't matter. So there's no loss of generality, at least at the moment, to call this the imaginary part of T. And it was reviewed in this very nice book by 2 of our organizers, that while this equation here makes the positivity of the imaginary part manifest, it doesn't really make the singularity structure of the amplitudes manifest. So often it's convenient to, there's missing a 1/2 here, to insert a complete basis of state x here. And if I was to sandwich this equation between out and in state, I would get this equation, which should look familiar for most of you. And in perturbation theory, this equation is actually very useful and gives rise to the so-called Gutkowski equation, which tells us that the imaginary part of a Feynman diagram is just equal to the sum of cuts that basically separate it into disjoint components. That's a very powerful equality. So the first thing I want you to remember, and most of you already know this, is that the imaginary part of the amplitude has support whenever cuts themselves as support. And the location at which a cuts start contributing are called thresholds. Okay? And at these locations, the amplitude, of course, cannot be real analytic. And because of this, we will say that it is singular. So this points out to qualitative necessary condition for the amplitude to be singular. The first one being that the phase space of cuts opens up or closes down. These are equivalent statements. Or two, that cuts themselves become singular. And we will see that these qualitative necessary condition can be phrased algebraically without any reference whatsoever to the reality of momenta. So there was no loss of generality in me calling the left-hand side of the unitarity equation the imaginary part of T. And today's focus will be on Feynman graph G that is equal to AB that can be disconnected into two subgraph A and B via a two-particle cut, so via this cut here. And the invariants on which each A and B depends on are these scalar product involving K, the cut loop momenta, and big PA, which stands for all the incoming momentum, or big PB, which stands for the list of outgoing momenta. And just to make sure that we all understand what this classification means, this means that I'm not going to consider diagrams of this type, where it's impossible to only cut two propagators and separate the diagram into two disconnected parts. But these type of diagram clearly fall into this classification, because I can just cut this gluon and this gluon, and I'm disconnecting the diagram into two separated parts. And you can write this as an integral over the independent scalar products between the loop and external momenta. So these basically XA and XB. And this expression should be familiar for everyone who knows about the Bykov representation of Feynman integrals. But if you don't, you should feel free to ask me later to fill out the details. So these are basically all the definition I'm going to skip over. But in the meantime, let me just give a somehow illustrative example. So we have this blob pattern here, and I'm just embedding this parachute graph that we will revisit later on into this blob picture. So A is just a vertex. B is just the bubble integrand. The measure is over these scalar products, and there's two delta function that takes into account the cut here. And G is the gram matrix of, so basically the matrix of scalar product between these independent loop and external momenta. Yeah, and the only thing you need to know about gamma is that its boundary is defined by det G equals 0. That's the only thing you need to know for the moment. So now we can come back to these qualitative necessary conditions for the amplitude to be singular. So what does it mean for two-particle cut? Well, point one means that at thresholds, the phase space gamma, so basically the integration contour, closes down to a single isolated point, which means that only classical scattering is possible. So this resonates with the Coleman-Norton picture of singularities. And in the space of leftover integration variable on the two-particle cut, this basically means that the boundary of the integration contour, which is, as I said, defined by dit G equals 0, collapses to a point. So it collapses from all directions. I'm going to give the algebraic conditions that correspond to this soon. Yeah, and point two, which some people call double discontinuities. So when the cuts are singular, basically happen when the singular locus of B, of A or B, so LA or LB, pinches the contour. So this corresponds to this case here, or it's the boundary of the integration contour. So this would correspond, for example, to an endpoint singularity. But physically, we never expect this case to happen, at least in momentum space, without det G itself equal to 0. And this is corroborated by Landau's analysis which tells us that on the singularity, the loop momenta is actually a linear combination of external momenta. So this det g equals 0 is satisfied. And even if you try very hard to implement this condition and try to see if it gives any new singularity, in all the examples we checked, it never does. So there's physical reason to ignore this case, and there's also all the example considered, it never gave something non-trivial. So basically, we'll just consider this case and case 1. And yeah, so at this point, we can find algebraic necessary condition for these two conditions to find the singularities of the Feynman graph, and they can be obtained uniformly as follows. So the first thing we need to do is to pick a possibly empty subset S of singularities on the left and on the right of the cut. Then we localize on the two-particle cut and on the locus S equals 0, which fix dim S variable from this two-particle cut. And this leaves us with a set XS of independent variables, in terms of which now the boundary is defined by this det G tilde equals 0, and G tilde is just the restriction of G to the two-particle cut and the singular locus S. And to ensure that there is no direction in which we could deform the contour of integration to avoid the singularity, we need to ask both det G tilde to vanish and also all of its derivative in the remaining variable in XS. And this system is nice because there's always one more equation than unknowns. So it means that the system will always give you an algebraic constraint on the kinematic space. So there will be no k.p involved at the end of the day. And basically, this condition is what I call LABS equals 0. So this is what PLD would find, for example. And to find the remaining singularities of A and B that are contained into this two-particle cut, we simply loop over all the set S of some amplitude singularities, and that, of course, includes the subtopologies. But the focus of today is really on the full graph. So it's basically on all the singularities that are accessible from the maximal cut. So this is commonly called leading singularities. Yeah. And at this point, there's a natural question that arises. We just saw that the necessary condition for singularities requires to know both LA and LB equals 0. And now we can just ask, can these be constructed recursively? And if either A or B are two-particle reducible, which means that they have a two-particle cut, the answer is yes. And you just repeat the same arguments over the blobs. So, oops. So to be more concrete, what I'm saying is that, say, B1 has a two-particle cut, so the diagram's hidden in B1 as a two-particle cut. Then you just repeat the argument for B1. So you extract B1, you take another two-particle cut that gives you a new Bykov representation integral, where basically all the subscript 1 quantities are replaced by subscript 2 quantities, and this power also changes, but it doesn't matter. The point is that the singular locus of B1 is given by solving the same set of equations, but where now G1 is replaced by G2. And you can continue this recursion until there's no two-particle cut anymore. So at the end of the recursion, you're left with either two things. So the first option is a collection of treatable subgraph, which makes the recursion very efficient and I would say systematic. And the other option is that there's some loop that are contained in the collection. And by loop, I mean loop that cannot be cut by a two-particle cut. And in this case, we may need, in fact, we need some extra inputs about the singularity structure of these non-two-particle cut reducible subgraph. But at low loop, I would argue that this is not very a problem. We can use, for example, Sebastian's package PLD as a seed of our recursion. Yeah, so this is a bit formal, and now what I want to do is to illustrate all this work in practice. And what I find nice about it is that it really boils down to like taking derivative, computing determinant. There's nothing fancy, really. So yeah, let me talk about this generic kinematic parachute graph. So what I mean by generic kinematic, basically mean that all the masses in the propagators are different, and all the square masses outside are also different. And the question we ask is, what are the candidate leading singularities, which means what are the singularities that are accessible from the maximal cut? So we start the recursion by looking at this two-particle cut. So we cut the triangle loop. So that gives us a Bikov-like expression where this constant here, so it's constant in the loop, but it's not constant in the external kinematic. So of course, this thing can give the singularity. The integration measure is just this, where we have two delta functions that takes into account this two-particle cut. A1 here is just a vertex. So in particular, it cannot give rise to any kinematic singularities. G1 is this matrix here. It's the gram matrix here. And OK, we don't see it at all somehow, but this is supposed to be blue. And this is also, so this and this is blue, and this is red. And these are fixed by the delta function. And there's one remaining kinematic invariance that depends on K1. And basically what we want to do is to fix it by localizing on the singular locus of the bubble. Okay? And we do this by repeating the same argument, but now over the bubble. So we get a new integral, there's some overall factor, some measure, and now both A and B are trivial vertices, so they don't give any new kinematic singularity. And G is just this 2x2 matrix. Again, we won't see. Yeah, we won't see. But all these entries that depends on K2, they are fixed by the two delta function here. And asking the determinant of this to be 0 gives us the first component of the singular locus of B1, which practically translates into this restriction on K1 the P3. And the only thing we need to do to get the leading singularity is to plug this expression here. So if we do this, this is what we get. And if you expand the determinant, you find a match with PLD. And at this point, you can ask, OK, what about other singularities accessible in the maximal cut? So on the previous slide, what we did basically is that we localized G1 in the bubble leading singularity, so on this normal threshold. But nothing stops us in general to localize on other singularities of B1. So on say, the second component of the singular locus, which I just identified with the second type singularity at alpha squared equals 0. And the effect of doing this is basically that K1.P3 equals something else. So it's different from the other slide. But nevertheless, when we plug it here, that's what we get. And if we expand the gram determinant, we get the singularity that hyperints find. And both of these singularities are the only non-trivial singularities that are accessible from the maximal cut. Okay? And yeah, what I wanted to do is just to emphasize that this approach is recursive. We can look at the L-loop diagram. So the massive panda ladder here, all the blocks here are massive. The external momenta are massless, but there's no obstruction in putting masses. So again, this should be blue, so it's a bit hard to see. But yeah, you can start the recursion by finding the singularity of the box by considering these two-particle cut. You can then use this information to end this two-particle cut to find the singularity of the double box, and so on and so on. And in doing so, you see a clear pattern. So basically, we find that the leading singularity of the L-loop panda ladder is the same as the one for the ladder. So basically for this graph here, but where now the t-channel variable is basically replaced by the solution to this polynomial. And you may notice that there are roots in this expression, and that's basically just because I made a choice of branch. Otherwise, the answer is not very compact. And if you really want the polynomial, you can just use the fact that this is equal to 0 here. Put all the roots on one side, square it, and do something like this until you don't have any roots. And I think in the ancillary file, we give like a 21 loop expansion where there's no root. OK. So in the time that I have left, I wanted to enumerate some checks and some new analytic predictions that we're able to make. And in this slides, I'm gonna display sequentially basically the two-particle cut we use in the recursion, just to make sure that everyone understands what I'm doing. So for the massive ACK node, it actually does not really matter. Like I can start with this two-particle cut or this two-particle cut in either order. It doesn't matter. Because the diagram is symmetric, but it's a bit less obvious for diagrams like this, where you have basically a non-planar loop. So for example, if you try to make a two-particle cut here, the algorithm will not work. What you need to do is really to cut these two propagators first, then use crossing symmetry to untwist the loop. And then you're allowed to cut this propagator and this propagator. So the order and for this diagram is important. And similarly, we can do similar thing for other diagrams. And in all these cases and other that we haven't put, we find a match with PLD and the existing literature. And these are examples of new predictions we made. And by new prediction, I basically mean examples in which we are not able to compare with any existing results from any existing method in useful time. And in most cases, you see that basically the diagram considered are just generalization, so more masses or more particles outside than the one that were considered, for example, by Sebastian. So for example, this diagram depends on 18 kinematic scales, which is a lot. Yeah. So and by the way, if you open the paper, you can just click on these little GitHub symbol to see the explicit polynomial. Yeah. But before I conclude, I wanted to give you an idea of how crazy these things can get. So this is the generic kinematic pentabox. So as I said, there's 18 variables. Kinematic variables. So this is just a sample in the background of how the polynomial looks like. This is just a zoomed in version, just to show like what kind of variables are involved. Yeah, this is just showing some terms, but there's about a million other terms that this file contains. And its size is about 40 megabytes. And just to give an order of magnitude, I asked ChatGPT to compare this to the size that the whole Harry Potter book series takes, and its conclusion is basically that is about the same order. So I just find it pretty amazing that a two-loop diagram can give a polynomial as big as that. It's probably a bad news for the symbol person, but I don't know. Yeah. So yeah. So let me conclude. In this talk, we introduced, I would say, surprisingly efficient unitarity-based method to extract the singularities of Feynman integrals. We stress tested the method against cutting-edge tools like apparent and especially PLD, and made new predictions for multi-loop processes, including many examples relevant for the standard model. And of course, there's many future directions, one of which I did not include, but there's clearly some link that would be nice to make with the story by Offie and Andrew. But other than this, I think it would be really interesting to find a systematic way of including higher cut subgraphs, so basically cuts that are not separable with a two-particle cut, without having to rely on PLD or the prior knowledge of their singularities. It would also be useful to see if there's a way to reconstruct the Schwinger parameter recursively, just to say if this or that singularity is on the first sheet or not. I think that could be useful for symbol people. Yeah, I think for the more mathematically oriented people, it would also be interesting to see if there's a way just to prove or disprove whether or not this procedure really captures all the singularities of a diagram. But in all the examples we checked, this seems to be true, but we don't have a solid proof of this. And this is probably an homework for myself, just to get better at solving a high degree polynomial equation. So basically, at getting better at computing discriminants in many variables. On that, I would like to thank you all for your attentions.
Thanks a lot for that very nice talk. Matthew, see a question over here.
Thanks for this nice talk. I could imagine that if you sum all the diagrams, like at the level of the amplitude, you would find some cancellations of these singularities. Is this something you expect or look at the moment?
I mean, I'm sure this can happen, and I'm sure there are examples where this happen. But yeah, I don't see immediately how this method would tell you this without explicitly computing the singularities of each diagram individually. But yeah, I think this happens. So for example, I've learned this week that there's work by Z. Byrne about like gravity diagrams where there's some elliptic structure that appears, and when they sum the whole thing to compute the amplitude, the elliptic structure disappears. So I guess there's also some singularity that disappear in this. So that can definitely happen. But yeah, I'm not sure how this help regarding this specific question.
Any other questions?
What does your method give for pure glue vertex?
Sorry?
What does your method give for pure glue vertex? Pure glue QCD vertex.
Pure glue vertex?
Yeah, like when you have only gauge field.
You mean like just gluon scattering?
Yeah, but at all polar, I mean, like.
Maybe just the all massless case.
Yeah, like things like this.
No, just three gluons. Like.
I mean, I would need to do the calculation to answer the question, but I mean, in general, you mean like a 3-point amplitude with gluons?
Yeah, 3-particle amplitude, but your orders. Do you have some
I would need to do the calculation, but we can definitely look at this. Yeah.
And what about like single phi cube theory?
I mean,
single mass.
All these should apply. So basically, if you have a diagram and you can express it as a in the Bicov representation, you can apply this. So it's theory agnostic.
We have another question over here.
Thank you very much for the talk. I think I have two questions. One is because when we investigate the integrals and we find some of the singularity just appear in the as the coefficient in the IPP reductions, but it do not appear as a letter or in the canonical differential equations. Then the thing is, how can you distinguish the letter or the singularities whether it appears in the differential equations?
You're talking like about spurious singularities? Like, are you talking about singularities that are not captured by the Landau equation? Like,
yes.
Yeah, I don't know what to say about these.
Okay. And the other question is...
I mean, they're unphysical, so you should not have to worry about them. Like, they should cancel somehow. Like, they should not be important if they're not captured by Landau equations. Maybe I'm not understanding the question.
Okay, maybe you can discuss later.
Yeah.
Maybe I have another question is, because if you look at your last diagram, and do you, because...
Which one?
Last box. And if we shrink the propagators and up and down, and how do you, because it is a subsector integrals, and can you still use your method to predict the singularity of subsector?
You need to draw it.
We should do.
Yeah.
Okay. Let's thank Matthew again for a great talk.